We're going to finish up chapter 5 today with sections 8 and 9. Finish up sequences, mathematical induction, and recursion. This one's a mouthful. Second order linear homogeneous recurrence relations with constant coefficients. Now, what in the world does that mean? Not obvious from what it's saying, but a second-order linear homogeneous recurrence relation with constant coefficients is a recurrence relation of the form A sub k equals big A sub big A times little a sub k minus 1 plus big B times A sub k minus 2 for every integer k greater than some fixed integer, where A and B are fixed real numbers and B is not equal to 0. So, are these second-order linear homogeneous recurrence relations with constant coefficients? It looks like the A is, B is not, because it's 3 terms. C is, because the even fractions are real numbers, so those are constants. D is nonlinear, so it's not, it doesn't fall into this category. E is a second order because A is 0, but B is not. So E should be a second order. F is not because it doesn't have the second term, F sub k minus 2. G is because with the constants 1 and 1. And H is not because k minus 1 is not a constant. So let's see if I got those right. Yes, no, yes, no, yes, no. Not homogeneous. And yes and no, non-constant coefficients. Yeah. The distinct roots case. Let A and B be real numbers. A recurrence relation of the form A sub k equals big A sub times A sub k minus 1 plus B times A sub k minus 2. It is satisfied by the sequence 1 t squared, t cubed, etc. 2 to the n, t to the n, where t is a non-zero real number if and only if t satisfies the equation t squared minus at minus ab or minus b equals 0. Getting kind of thick with the math here. Why would they do that in a math class? But given a second-order linear homogeneous recurrence relation with constant coefficients, the characteristic equation of the relation is t minus at minus b equals 0. So it has a characteristic equation for the relation. Consider the recurrence relation that specifies that the kth term of the sequence equals the sum of the k first term plus twice the k minus 2 term. That is, a sub k equals a sub k minus 1 plus 2 a k minus a sub minus k minus 2. Find all the sequences that satisfy the relation and have the form 1 t squared, t cubed, etc., tn to the n onto infinity, where t is non-zero. Well, by lemma 581, the relation is satisfied by the sequence if t satisfies the characteristic equation t squared minus t equals, or minus 2 equals 0. Since t squared minus t minus 2 equals t minus 2 times t plus 1, the only possible values of t are 2 and 1, minus 1. It follows that the sequences 1, 2, 2 squared, 2 cubed, etc., and minus 1, or 1, minus 1, minus 1 squared, minus 1 cubed, etc., are both solutions for the relation, and there are no other solutions of this form. So it follows that the sequences are both solutions for the relation, and there are no other solutions of this form. Note that the sequences can be written more simply as these series of numbers here: 1, 2 squared, 1, 2, 2 squared, 2 to the third, 2 to the n, minus 1, minus 1, minus 1, 1, minus 1, etc. So, if R0, R1, R2, etc., and S0, S1, S2, etc., are sequences that satisfy the same second-order linear homogeneous recurrence relation with constant coefficients, and if C and D are any numbers, then the sequence A is defined by the formula A sub n equals C times Rn sub n plus D times S sub n for every integer n greater than or equal to 0. This also satisfies the same recurrence relation. So consider the recurrence relation that specifies that the kth term of the sequence equals the sum of the k minus first term plus twice the k minus 2 term. Find a sequence that satisfies the recurrence relation that also satisfies the initial conditions. A sub 0 equals 1 and A sub 1 equals 8. So the sequences are from the previous example. Both satisfy the relation, although neither satisfies the given initial conditions. However, by lemma 582, any sequence A that satisfies the explicit formula C times 2 to the n plus D times minus 1 to the n, where C and D are real numbers, also satisfies the relation. You can find C and D so that sequence A satisfies the initial conditions specified in this example by substituting n equals 0 and n equals 1 into the equation and solving for C and D. So when you simplify, you obtain the system 1 equals C plus D, and 8 equals 2C minus D, which can be solved in various ways. For instance, if you add the two equations, you get 9 equals 3C, and so C equals 3. Then by substituting into 1 plus c plus d, 1 equals c plus d, then you get d equals minus 2. It follows that the sequence A given by this recurrence relation, or by this equation, equals 3 times 2 to the n minus 2 times minus 1 to the n for each integer n greater than or equal to 0. This satisfies both the recurrence relation and the given initial conditions. So the distinct roots theorem, it says that if suppose a sequence A satisfies a recurrence relation, A sub k equals big A times A sub k minus 1 plus B times A sub k minus 2 for some real numbers A and B, with B not equal to 0, and every integer k greater than or equal to 2. If the characteristic equation has two distinct roots, R and S, then the sequence A is given by the explicit formula A sub n equals C times R to the n plus D times S to the n, where C and D are the numbers whose values are determined by the values of A0 and A1. So you can solve it all with by manipulating stuff around and finding what the sequence, determining what the sequence is. The Fibonacci sequence satisfies the recurrence relation f sub k equals f sub k minus 1 plus f sub k minus 2 for every integer k greater than 2, with the initial conditions f0 and f1 are equal to 1. Find an explicit formula for this sequence. Well, the Fibonacci sequence satisfies the first part of the hypothesis of the distinct roots theorem, since the Fibonacci relation is a second-order linear homogeneous recurrence relation with constant coefficients, being 1 and 1. To check that it satisfies the second part of the hypothesis, examine the characteristic equation. T squared minus t minus 1 equals 0. By the quadratic formula, t equals this mess here. So the roots are distinct. And thus it follows from the distinct roots theorem that the Fibonacci sequence is given by the explicit formula f sub n equals c times 1 plus the square root of 5 over 2 to the n plus d times 1 minus the square root of 5 over 2 to the n, where c and d are the numbers whose values are determined by the fact that f0 and f1 are equal to 1. To find c and d, you write it out and do your substitutions and for the values of f0 and f1. And then solve for C and D. So it may look complicated, but in fact is just a system of two equations and two unknowns. Solving the two system of equations, we get C equals 1 plus the square root of 5 over 2 times the square root of 5, and D equals minus 1 minus 1 minus square root of 5 all over the square root of 2 times the square root of 5. By substituting these values for C and D in the formula, gives this, and simplifying it gives you this here for each integer n greater than 2, or greater than 0. Remarkably, even though the formula f sub n involves the square root of 5, all the values of the Fibonacci sequence are integers. So, the single root case. Let a and b be real numbers and suppose the characteristic equation t squared minus at minus b equals 0 has a single root r. Then the sequences r and 1 r squared, r to the first, r to the second, r to the third, r to the n, and 0 r, 2r squared, 3r cubed, etc. to n r to the n. Both satisfy the recurrence relation a sub k equals big A times little a sub k minus 1 plus b times a sub k minus 2 for each integer k greater than or equal to 2. Then the single root theorem states that suppose a sequence A satisfies the recurrence relation for some real numbers a and b with b not equal to 0 for every integer k greater than or equal to 2. If the characteristic equation has a single root r, then the sequence of A is given by the explicit formula A sub n equals C times r to the n plus d times n to the r to the d times n times r to the n, where C and D are real numbers whose values are determined by the values of A, 0, and any other known value of the sequence. So suppose the sequence B satisfies the recurrence relation. B sub k equals 4b sub k minus 1 minus 4b sub k minus 2 for every integer k greater than or equal to 2. With the initial conditions b sub 0 equals 1 and b sub 1 equals 3. Find an explicit formula for the sequence B. This sequence satisfies the first part of the hypothesis of the single root theorem because it satisfies it is a second order linear homogeneous recurrence relation with constant coefficients. The single root condition is also met because the characteristic equation t squared minus 4t plus 4 equals 0 has a unique root r equals 2. R equals 2. It follows from the single root theorem that b is given by the explicit formula b sub n equals c times 2 to the n plus d times n times 2 to the n, where c and d are real numbers whose values are determined by the fact that b sub 0 is equal to 1 and b sub 1 equals 3. Find c and d. Write out the substitutions for the values of b sub 0 and b sub 1 and solve for c and d. So c equals 1, and then d equals 1/2. Now substitute c is equal to 1 and d equals 1/2 into formula 5, 8, 12 to conclude that b sub n is 2 to the n times 1 plus n over 2 for each integer n greater than or equal to 0. And that'll be it for that section. And I didn't trip over that big long title at the beginning once. I think that's a first. But let's see here. All right. Last section. General recursive definitions and structural induction. Sequences of numbers are not the only objects that can be defined recursively. In this section, we discuss recursive definitions for sets and functions. We also introduce structural induction, which is a version of mathematical induction that is used to prove properties of recursively defined sets. So, recursively defined sets. To define a set of objects recursively, you identify a few core objects as belonging to the set and give rules showing how to build new set elements from the old. More formally, a recursive definition for a set consists of the following three components. A base, a statement that certain objects belong to the set. Recursion, a collection of rules indicating how to form new set objects from those already known to be in the set. And then the restriction, a statement that no objects belonging to the set other than those coming from the base and the recursion. The set of Boolean expressions was first introduced in section 2.4 as legal expressions involving letters from the English alphabet, such as A, P, Q, and R, and the symbols for and, or, and not, and parentheses. To make precise which expressions are legal, the set of Boolean expressions over a general alphabet is defined recursively. The base is each symbol of the alphabet is a Boolean expression. Recursion. If P and Q are Boolean expressions, then the following are also Boolean expressions. P and Q, P or Q, not P, and P in parentheses. Restriction. There are no Boolean expressions over the alphabet other than those obtained from the base and the recursion. Derive the fact that the following is a Boolean expression over the English alphabet A, B, C, D, etc. to Z. Not P and Q, or not O, R and P. By 1, P and Q and R are Boolean expressions. By 1, 2A and 2C, P and Q and not R are Boolean expressions. By 2 and 2D and 2A, P and Q in parentheses and not P or not R and P are Boolean expressions. By 3, 2C and 2D, not P and Q and not R and P in parentheses are also Boolean expressions. And then finally by 4 and 2B, the full expression is a Boolean expression. Certain configurations of parentheses in algebraic expression are legal, and whereas others are not. They got to match up. Opening parentheses have got to have a matching closing, and vice versa. Here is a recursive definition to generate the set C of legal parentheses structures. Base, is open and close is in C. Recursion 2A. If E is in C, so is E in parentheses, opening and closing. If E and F are in C, so is E times F. So is EF. Restriction. No parentheses structures are in P other than those obtained from the base and the recursion. Show that this here is a parentheses structure in C. By one open and close is in C. By 1, 2, and 2A, 2 open and 2 closed is in C. By 2, 1, and 1B and 2B, 2 open, 2 closed, 1 open, 1 closed is in C. And recursion is used to give a formal definition for the set of all strings over a finite set. Recursive definition for the set of all strings over a finite set. Let A be any finite set. Call the elements of A characters, and define the set of all strings over A as follows. Base. Lambda is a string in S where lambda denotes the null string, the string with no characters. 2. Recursion. New strings are formed according to the following rules. If U is any string in S, and if C is any character in A, then UC is a string in S, where UC is called the concatenation of U and C, and is obtained by appending C to the right of U. Recursion 2B. If U is a string in S, then both the concatenation of lambda and U, denoted by lambda U, and the concatenation of U and lambda, denoted U lambda, are defined to equal U, symbolically here. Recursion 3C. If U and V are any strings in S, and if C is any character in A, then the concatenation of U and VC is defined to be equal to the concatenation of U, V, and C, like so. Basically, the associative property applies. Restriction. Nothing in string S other than the objects obtained from the base and the recursion are in the set. The base for the recursive definition of strings only indicates that one character, namely lambda, is a string. The next theorem states that each individual character in the underlying set is a string as well. Theorem 591 is if A is a finite set and S is the set of all strings over A, then every character in A is a string in S. Suppose A is a finite set. S is the set of all strings over A, and A and B are in A. Because of the way the definition of strings is stated, it cannot be deduced immediately that B parentheses A is a string in S. Prove that this is true, first show that BA and BA in parentheses concatenated with A are strings in S, and use the fact that B open parentheses AA close parentheses equals open parentheses B A close parentheses A. So you go through the solution here. Theorem 591. A and B are both strings in S because both A and B are in A. By 1 and 2A, BA is a string in S because B is in S and A is an element of A. By 2 and 2A, BA is BA is a string in S because BA is an element of string and A is an element of string. By 2C, BAA and BAA are the same because B and A are strings in S and A is an element of A. By 3 and 4, BAA is a string in S because it equals BAA, which is also a string in S. Proving properties about recursively defined sets. When a set has been defined recursively, a version of mathematical induction called structural induction can be used to prove that every object in the set satisfies a given property. So, the process. Let S be a set that has been defined recursively, and let P of X be a property that objects in S may or may not satisfy. To prove that every object in S satisfies P of X, perform the following two steps. Show that P of A is true for each object A in the base for S. Show that for each X in S, if P of X is true, and if Y is obtained from X by applying a rule from the recursion, then P of Y is true. To perform this step, suppose that X is an arbitrarily chosen element of S for which P of X is true. This is the inductive hypothesis. Then show that if Y is obtained from X by applying a rule from the recursion of for S, then P of Y is true. Conclusion. Because no objects other than those obtained from the base and the recursion are contained in S, steps 1 and 2 prove that P of X is true for every object in object X in S. So let S be the set of all integers defined recursively as follows. Base 4 is in S. Recursion. Given any integer n in S, n plus 3 is in S as well. Restriction. No integers are in S other than those derived from the base and the recursion. Use structural induction to prove that for every integer n in S, n mod 3 equals 1. Proof by structural induction. Given any integer n in S, let property P of n be the sentence n mod 3 equals 1. Show that P of n is true for each integer in the base for S. The only object in the base is 4, and P of 4 is true because 4 mod 3 is 1. Show that for every integer n in S, if P of n is true, and if m is obtained from n by applying a rule from the recursion for S, then P of m is true. Suppose n is any integer in S such that P of n is true. Then n mod 3 is equal to 1. The recursion for the S consists of only one rule, and when it is applied to n, the result is n plus 3. To complete the inductive step, we must show that P of n plus 3 is true. by inductive hypothesis, n equals 3k plus 1 for some integer k. It follows that n plus 3 mod 3, or 3k plus 1 plus 3 mod 3 equals 3k plus 4, which is 3k plus 1 mod 3, which is equal to 1. So yeah. All right. Conclusion: because there are no integers in S other than those obtained from the base and the recursion for S, every integer n satisfies, and every integer in S satisfies the equation n mod 3 equals 1. So n plus 3 mod 3 equals 3k plus 1 plus 3 mod n, or mod 3. And there's a typo here. That's supposed to be 3k plus 1 plus 3. So a recursive definition can also be given for the length of a string. Given the set of all strings S over a finite set A, the length L of a string in S is defined as follows. Length of lambda equals 0. For every string in U in S and every character in A, the length of UA is 1 more than the length of U. So the length of UA equals the length of U plus 1, where U is an element of S and A is an element of A. The following theorem states that the length of a concatenation of two strings is the sum of the lengths of the strings. If S is the set of all strings over a finite set A, then for all strings U and V in S, the length of UV equals the length of U plus the length of V. Next theorem extends the operations to two pairs of strings. The concatenation of any two strings is a string. If S is the set of all strings over a finite set A, and U and V are any strings in S, then UV is a string in S. And then this theorem generalizes the associativity of concatenation of any three strings. If S is the set of all strings over a finite set A, and U, V, and W are any strings in S, then U concatenated with V and W is equal to U and V concatenated with W. Recursive functions. A function is said to be defined recursively, or to be a recursive function, if its rule of definition refers to itself. Because of this self-reference, it is sometimes difficult to tell whether a given recursive function is well defined. Recursive functions are of great importance in the theory of computation in computer science. So the following function, positive m from positive integers to integers, was defined by John McCarthy in m of n is equal to n minus 10 for n greater than 100, and m equals m times m sub m of n plus 12 if n is less than or equal to 100 for all positive integers n. Find m of 99. You just do some substitution. And you get 91. So the remarkable thing about this function is that it takes the value 91 for all positive integers less than or equal to 101. That's showing that that's going to be exercise 24 at the end of the section. For n greater than 101, m of n is well defined because it equals n minus 10. In the 1920s, German logician and mathematician Wilhelm Ackermann first defined a version of the function that now bears his name. This function is important because its values are computable, but it cannot be evaluated using only for next loops. The function is defined on the set of all pairs of non-negative integers as follows. A of 0 and n equals n plus 1 for all non-negative integers n. A of m and 0 is equal to a of m minus 1 and 1 for all positive integers m. And a of m and n equals a of m minus 1 and a of m and a of m and n minus 1 for all positive integers m and n. So find a 1 and 2. A of 1 and 2. Yeah, a lot of substitution going on and simplifying, and end up with 4. The special properties of the Ackermann function are a consequence of its phenomenal rate of growth. While the values a of 0 and 0 and a of 1 and 1 and a of 2 and 2 and a of 3 and 3 are not especially impressive, a of 4 and 4 is 2 to the 2 to the 2 to the 65,536th power. And values of a of n and n continue to increase with extraordinary rapidity thereafter, as if that wasn't fast enough. Consider the following attempt to define a recursive function g from positive integers to integers for each integer n greater than or equal to 1. Well, g of n is equal to 1 if n is 1. G of n is equal to 1 plus g of n divided by 2 if n is even. And g of the 3n minus 1 if n is odd and n is greater than 1. Is g well defined? Now, suppose g is a function, then by definition of g of 1 is 1, g of 2 is equal to 2, g of 3 equals 4, g of 4 equals 3. However, when you get to g of 5, it is equal to g of 14, which is equal to 1 plus g of 20, which is equal to 3 plus g of 5. Subtracting g of 5 from both sides gives you 0 equals 3, which is false. So since the supposition that g is a function leads logically to a false statement, it follows that g is not a function. So you can use the processes of logic to determine if a function is well defined or not before you put it into code. Well, that'll be it for today. Just the 2 sections. Remember, the quiz on Chapter 5 will be on Thursday. I haven't checked. Is the homework due? Okay, I'm going to change it to due before the quiz. Due before class on Thursday. And then you can work on Chapter 9 after that. But anyway, have a good day. See you on Thursday. Have your notes prepared and print it out. So, see you next time.